Hey guys, this is the Chemistry Club, and today we're going to delve further into the concept of electron orbitals with the wave mechanical model by learning the notations for electron configuration and how quantum numbers work. So as a correction, in the last video I referred to the periodic table as having rows and columns. Technically speaking, rows are called periods and columns are called groups. However, I will keep referring to them as rows and columns because it is easier to visualize. Let's begin with the simplest form of electron configuration, which is just writing it out. The notation is simple. You write the principal energy level, then the subshell, then the amount of electrons in each group of subshells. As an example, let's do hydrogen. Since hydrogen has a principal energy level of 1, let's start by writing 1. And we also know that its only electron is in an s orbital, so we'll write s after the 1. And finally, we know that there is only one electron in this s group, and thus we write 1 afterwards. And for proper notation, the final number should be in superscript, which is basically an exponent. And the end result is 1s1. And now let's do something a little more complicated, like fluorine. We do atoms like this by going through all the electron shells that are in the atom, so we'll start with the 1s. We know that 1s shell for fluorine has both its electrons, so we'll write 1s2. Then we go to the 2s, same thing here, the 2s has all its electrons, so we write 2s2. Then we get to the 2p. We know that fluorine is the fifth atom in this row going from left to right, and thus we can say that 5 out of the 6 electrons in the 2p orbital group are filled, so we'll write 2p5. And when you combine these together, we get 1s2, 2s2, 2p5, which is the electron configuration for fluorine. So here's an example to practice on your own. Once I reveal the element, pause the video and work it out, and then compare your answer with what I have. Your element is antimony, or Sp on the table. So here's what I got. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p3. A common error for this one would be putting the 3d after the 3p and not the 4s. You want to make sure to always go from left to right on the table, regardless of how weirdly the d and f orbitals are placed. Now since this notation is really long and a bit useless because you end up listing a ton of orbitals that come way before the element, there is a way to shorten it. You just write the name of the noble gas that comes before the element in brackets, and then you do the notation for the row of the element. So let's do antimony again. Looking at the table, we see that krypton is the noble gas that comes before antimony because it's on the row above. So we rewrite Kr in brackets, and then list the electron configuration for the row that antimony is on. So we end up with Kr 5s2, 4d10, 5p3. And this hopefully makes your life a little bit easier as you do these. And another thing we can do with this notation is draw it out. This is a little bit more annoying than writing out the notation, but it does give you a good idea of how electrons are laid out in each atom. Before we start, there are a few rules we have to follow. The first is the Aufbau principle, which states that we have to start from lower energy shells and work our way up. In layman's terms, don't randomly pick an orbital like 4p and start from there. Instead, start at 1s and go to 2s, 2p, and so forth. Our next rule is the Pauli exclusion principle, which states that each orbital can only hold 2 electrons, and each electron has a spin of either 1/2 or -1/2. Basically, for each distinct orbital in each group of subshells, like how 1s is 1 orbital, p is 3, etc., this orbital can only hold 2 electrons, 1 with each spin. And we discussed this before, but this is the reason why. And finally, you have Hund's rule, which states that for each subshell, electrons prefer to be by themselves in each distinct orbital. For the d subshell, for example, if you had 5 electrons, they wouldn't sort themselves out into the 2 full orbitals and 1 half-filled one. Instead, what you see is that you have 5 half-filled orbitals. If you start adding electrons to this, then they start doubling up in the orbital. So if we have the same d subshell, but with 7 electrons, you would see 2 filled shells and 3 half-filled ones. And this is just a way for electrons to retain the lowest energy possible. So Now that we have these rules, here's an example of what the configuration looks like drawn out. As you can see, we start at 1s because of the off-ball principle, and we make sure to keep 2 electrons at max in each orbital because of the Pauli exclusion principle. And we draw our electrons as arrows going either up or down to represent the distinct spin or charge the electron has, which is again either 1/2 or -1/2. And keep in mind that we draw a line for each distinct orbital for each subshell and draw the 2 electrons in there. For this one, they do draw boxes, but lines are more than sufficient. And as we get up to where the subshell isn't full, you can see how Hund's rule is followed. We half-fill each orbital first. And you can see this most in the p areas. So for example, nitrogen, we fill up 3 p orbitals, we half-fill them up, and then for oxygen, then we start doubling up, because we have no more excess orbitals where we can only add 1 electron. And you get better at these with practice, so here's one to do on your own. Since this takes up a lot of time, I'll give a simpler one, cobalt. Alright, so here's what I got, or here's what the internet says. And if you miss something, make sure to adhere to the rules. So as you can see here, we follow the off-ball principle, going from 1s to 2s, and so forth. And we follow Pauli exclusion by having 2 electrons with different spins in each box. And lines, again, are sufficient, but this one uses boxes. And then, once we get up to the 3D, we follow Hund's rule and half-fill each shell first, and then start doubling up. The unfortunate thing about these rules is that they are not perfect. There are a few exceptions. However, the exceptions themselves are all basically the same. You remove 1 electron from the s orbital in the row and add it to the d subshell. So this is just a lower energy state for the electrons to be in. And the exceptions you're going to want to know are copper, silver, gold, chromium, and molybdenum. So here are some examples of what their configurations look like written out. Keep in mind I am using the simplified notation. Copper is brackets argon 4s1 3d10, and gold is brackets xenon 6s1 4r14 5d10. So even though both of these are the 9th element in the D group, we remove an electron from the S and add it to the D, and the other exceptions are all just like this. So our final concept for today is that of quantum numbers, which is just a notation that allows us to pinpoint exactly where an electron is in the atom. So the first is the principal quantum number. That's our principal energy level. That goes from 1, the topmost row, to 7, the bottom row. And this is indicated by N. The next one we have is the azimuthal quantum number, which indicates subshell. S is 0, P is 1, D is 2, and F is 3. And this is indicated by that curly L. And next we have our magnetic quantum number, M subscript curly L, which indicates orbital. For S, since there's only 1 orbital, the only magnetic quantum number is 0. For P, since there are 3 orbitals, we have -1, 0, and 1. The -1 orbital is the one on the furthest left of each group, or each subshell group. And for D, we have -2, -1, 0, and 2, and as you might have guessed, the -2 orbital is on the left. And finally, we have the spin quantum number, or M subscript S, which indicates the spin of electron, the number itself is either 1/2 or -1/2. For this one, the first electron we put in each orbital is positive. So remember, when you did the diagrams, you first put the positive one in, and then afterwards, when you start doubling up, you put the one facing down. So the first ones are positive, second one's negative. So let's do a few examples to make sure we have these down. Our first example is aluminum. For this one, since aluminum is on the 3rd row, its principal quantum number is 3. We know that it's in the p orbital, so our azimuthal quantum number is 1. Looking at our table, we see that it's on the furthermost left of the p group, so its magnetic quantum number is -1. And finally, since it only has 1 p electron, its spin is 1/2. So try calcium on your own. The correct answer is 4, 0, 0, -1/2. So as you can see, it's in the 4th row, so principal number is 4. And for azimuthal, since it's in S, it's 0. Magnetic, since there's only one orbital in S, again is 0. And then because it's the second one on the left, it's the one on the right for the S group, it's the one that is being added to double up in the shell. So the spin number is -1/2. So next time we will be covering significant figures and measurement. Hope to see you then.